Hey guys, welcome to this video. So in this video I'm going to discuss example 5 point no I'm going to discuss question 5.15. Question 5.15. In the previous class I discussed question 5.13, and in this class I'm going to discuss question 5.15. Let me just start inking. Let's work with a blue pen today. 3 point, yeah. So this is question 5.15. Question 5.15. Page 5.80. SC Gupta, Fundamentals of Mathematical Statistics. Sorry for my handwriting. Page 5.80. Right, so let's just start with it. This question has two parts. So part A says that we are given a random variable x, and the PDF associated to the random variable is fx kx e to the power minus lambda x kx e to the power minus lambda x is greater than equal to 0, lambda is greater than 0, and this is 0 otherwise. So this is not defined for any negative value of x or any negative value of lambda. Right, so we need to find k, the constant k, the mean and the variance. Mean, variance and the constant k. So now for finding k, we need to integrate this function over. So k is a constant, I'll just take it out. Fx dx 0 to infinity. Why? Because x is greater than equal to 0, and this implies that x belongs to 0 to infinity, right? So this is equal to 1. Now we need to solve this integral and then find the value of k. So this will be k x e to the power minus lambda x dx 0 to infinity equals 1. Now for solving this integral, I'll use eilate, and eilate says that we need to find the function. So this is exponential, this is algebraic, so this algebraic function becomes our first function. So our first function is x, our second function is e to the power minus lambda x, right? My PDF is x e to the power minus lambda x, right? My PDF is x e to the power minus lambda x, yes. So this is my first function, this is my second function. Now the formula, this is not a standard rule but we use it. So this says that, eilate says that the integral I is equal to the product of the first function with the integral of the second function minus the derivative of the first function I1 dash with the product of the integral of the second function dx and the whole integral of this, right? So then putting in the limits will give me my integral. So my integral is I I is equal to x e to the power minus lambda x dx. I'm just ignoring k for here for this time. So this becomes, the first function is x, so this x comes out. Now the second function e to the power minus lambda x upon minus lambda minus the derivative of the first function, which is 1, and the second function, the integral of the second function is e to the power minus lambda x minus lambda, and then dx, because we need to integrate this whole function. So the integral of e to the power minus lambda x is equal to e to the power minus lambda x upon minus lambda. The derivative of x is equal to 1. So this is it. So this gives me minus 1 upon lambda x to the power x into e to the power minus lambda x minus plus 1 upon lambda, and this, then integrating this e to the power minus lambda x gives me another lambda. So this becomes e to the power minus lambda x minus lambda. So this gives me minus 1 upon lambda minus plus minus becomes minus 1 upon lambda square, because I have two lambdas here, e to the power minus lambda x. Wait, I need to write this again. I'll write this on the next page. I'll just go to the next page, and this gives me, so my integral is now minus 1 upon lambda x e to the power minus lambda x minus 1 upon lambda square e to the power minus lambda x. Right. So now putting in the limits, because we were given that x lies between we were given that x is greater than or equal to 0, right? So just putting in the limits, this gives me minus 1 upon lambda. So this is 0 because e to the power infinity, this is e to the power minus lambda x. So wait, e to the power minus lambda x is 1 upon e to the power lambda x, and when x goes to infinity, e to the power minus lambda x goes to 0. Let me just write this clearly so that you guys can understand. So e to the power minus lambda x is equal to 1 upon e to the power lambda x. When x goes to 0, this e to the power minus lambda infinity, this becomes 1 upon e to the power infinity, which is equal to 0, right? So this whole is 0. This is 0 minus 1 upon lambda square into 0. Now now I'll be putting in 0 in the limit, so this becomes 0. If I put in 0 in place of x, and this e to the power minus lambda x, if I put 0 here, this becomes minus lambda into 0, which implies that this is e to the power, this becomes 0. So this is e to the power 0, which is 1. This is 0 because I had x here, so this becomes 0 minus 1 upon lambda square into 1, right? So this integral becomes, this is 0 minus plus, so 1 upon lambda square, right? So my integral is 1 upon lambda square, and I needed to find k such that k times the integral is equal to 1. So if I write this in a different way, or in the way that I explained you guys, this becomes k, and this was x e to the power minus lambda x 0 to infinity dx is equal to 1. I wrote this here, right? I wrote this here, right? This equation. So I was just solving the integral, and I defined I to be this, and I defined I to be this, 0 to infinity, right? So ultimately this becomes ki is equal to 1, k into this is 1, and I know that I is 1 upon lambda square, so this becomes k times 1 upon lambda square, which is equal to 1, which gives me k is equal to lambda square, right? We are done with this. Let's now find the mean. For the mean, I just need to find this x, fx dx, integrating this 0 to infinity. This gives me x 0 to infinity, where fx is k e. My fx was k e to the bar kx e to the bar minus lambda x, right? And putting in the value of k, which is lambda square, this becomes lambda square x e to the power minus lambda x, right? So now this becomes lambda square x e to the power minus lambda x dx. This becomes 0 to infinity x, lambda square comes out because it's a constant term. This becomes x square e to the power minus lambda x dx, and this becomes lambda square out, and this whole becomes, now x square comes out. This is the first function, integrating the second function, minus lambda minus the derivative of the first function, which is 2x, and the integral of the second function, which is e to the power minus lambda minus lambda, right? And this becomes lambda square x square minus sign e to the power minus lambda x, and just lambda here because I transferred this minus here in the numerator. This becomes 2 times 2 comes out, it's a constant term. Now integrating this again like I did previously, this becomes x is the first term. I'm just taking out minus lambda here, so this becomes minus plus. Lambda comes out, this becomes x, and x is the first function. My e to the power minus lambda x is the second function, x e to the power minus lambda x. This is minus lambda here, minus the derivative of the first function, which is x, and this is 1, e to the power minus lambda x, the integral of the second function, and then integrating the product of these. Now this ultimately gives me lambda square minus x square e to the power minus lambda x, and lambda in the denominator, and this gives me plus 2 upon lambda x e to the power minus lambda x upon minus lambda. This becomes minus lambda, this is positive. So see, this is positive, and if I take this lambda out and then integrate this gives me, this term becomes, and this negative sign, this becomes positive 1 upon lambda. This minus plus lambda comes out, it's a constant term, and then integrating this gives me e to the power minus lambda x upon minus lambda, which becomes minus 1 upon lambda square e to the power minus lambda x, right? So just finally this becomes minus 1 upon lambda square e to the power minus lambda x, right? So this becomes minus x square, so this becomes minus x square e to the power minus lambda x upon lambda plus minus 2 upon lambda square x into e to the power minus lambda x minus 2 upon lambda cube e to the power minus lambda x. Now putting the limits 0 to infinity, lambda square, putting infinity here, no, yeah, so this becomes 0, e to the power minus infinity, e to the power minus infinity, e to the power minus infinity. The first term becomes 0 minus, now putting in 0 in place of x, 0, 0, this is 0, this is 0. Now this is minus 2 upon lambda cube, minus 2 upon lambda cube into 1, which gives me lambda square, minus minus positive, 2 upon lambda cube, which gives me 2 upon lambda. So my mean is 2 upon lambda. Hmm. 2 upon lambda. This is 2 in the numerator, and this is lambda in the denominator. 2 upon lambda is my mean. So let's find the variance. They haven't given us the answer to this. This is part of the back exercise, but they have given the answer to the B part. They've just written the answers. There's no solution. That's why I'm solving this. Earlier I was discussing examples, so they had given the solutions, but the solutions weren't as descriptive enough. So variance, I mean, they were descriptive, but it's better if all of the steps are defined. They skip some of the steps. They expect the student knows this. So the variance is, the formula of the variance is ex square minus ex whole square. We have already found this, so we need to find ex square, or x square fx dx. So my PDF was fx was lambda square x e to the power minus lambda x. So this gives me x square, and lambda comes out, lambda square into x e to the power minus lambda x dx, 0 to infinity, e x square, x, this becomes x cube. So this is lambda square, this is x cube, e to the power minus lambda x dx, again 0 to infinity, this becomes lambda square. Now this is x cube, e to the power minus lambda x minus lambda. This is big, so this becomes the derivative of the first function, and the integral of the second, and the product, and the integral of the whole product. This becomes minus, this becomes minus, and this becomes positive. So this gives me lambda square x cube e to the power minus lambda x minus lambda plus 3 comes out, x square e to the power minus lambda x so this becomes x square minus lambda comes out, lambda is a constant, lambda comes here. So x square, the first function as it is, the integral of the second function, which gives me e to the power minus lambda x minus lambda again, plus minus the integral of this, the derivative of the first function 2x. 3 I had already taken out, so 2x, the derivative of x square, and earlier we needed to find the derivative of x cube, which was 3x square. Now the derivative of x square, because I have already taken out 3 common from this integral. We are solving this integral, so this is as it is, this comes here, so this is minus 2x. Now again the integral of the second function and the product, and the integral of the product, so this becomes minus positive plus, now this becomes minus here, minus x cube e to the power minus lambda x upon lambda, and I'm just opening this bracket, so this becomes minus 3 upon lambda square, lambda x square e to the power minus lambda x. Now 3 goes here, so this becomes 3 upon lambda, and I take this lambda and this 2 outside, so this becomes 2 upon lambda, and integrating this function e to the power minus lambda x into x. This was the first. Now again, wait, let me just write this in the correct form. This is x e to the power minus lambda x dx. Going to the next page. Now this was 3 and this was 2. This was 2, not lambda. I hope you guys can understand me. 3 upon lambda into 2 upon lambda. 2 and lambda comes out. So this becomes 6 upon lambda square. So this was 6 upon lambda square. Now integrating x. Now integrating this function. Right? This function. So we have already integrated this earlier. So this just becomes this first function as it is, the integral of the second function minus the derivative of the first function, which is x. So this becomes 1 into e to the power minus lambda x upon minus lambda, and then we'll integrate this, and another negative positive. This becomes 1 upon lambda, and 1 upon lambda comes out, and then integral of this e to the power minus lambda x, and this gives me e to the power minus lambda x, and another minus lambda here, and this is positive because minus was cancelled. So this becomes minus 1 upon lambda square e to the power minus lambda x. We have already done this in the previous parts, e to the power minus lambda x. So I'm just erasing this. I was just explaining you guys again so that you don't get confused. I'm just erasing all of this. We don't need all of this. I'm just writing the answer directly. Right, so this is minus plus, and this again minus. So this was e to the power minus lambda x upon lambda square. Now I need to put in my limits. My limits were 0 to infinity, so this becomes, now putting in, let me just write this clearly. We had lambda square here, right? So lambda square here, lambda square. So this was minus x cube e to the power minus lambda x upon lambda minus 3 upon lambda square x square e to the power minus lambda x plus 6 upon minus 6. Wait, this becomes plus and minus 6 upon lambda cube e to the power minus lambda x into x, and this is negative, so negative 6 upon lambda to the power 4, lambda square, positive negative e to the power minus lambda x. Now my limits are 0 to infinity. This ultimately gives me, so putting in infinity gives me 0, 0, 0, 0. All of the terms with e to the power minus lambda x become 0. Now putting in 0, all the terms with x become 0. So this becomes 0, this is 0, 0, but this is minus 6 to the power lambda upon lambda to the power 4, minus 6 upon lambda to the power 4 into 1, because e to the power minus 0 is 1, e to the power 0 is 1, so this comes here, yes. So this becomes lambda square, minus 1 is positive, this becomes 6 upon lambda to the power 4, cancelling this gives me 6 upon lambda square. So e x square is equal to 6 upon lambda square. Now my variance is e x square minus ex whole square. My variance is 6 upon lambda square. On the previous part I found this, which was equal to 2 upon lambda, right? So 2 upon lambda, 6 upon lambda square minus 2 upon lambda minus the whole square of 2 upon lambda, 2 upon lambda. This gives me 6 upon lambda square minus 4 upon lambda square. Taking the LCM, this gives me 2 upon lambda square. So my variance is 2 upon lambda square. So my variance is 2 upon lambda square.